So when we first introduced Newton's laws, we did the dynamics piece first, F net equals ma, and then we came back and added on the kinematics. But part of what I wanted to emphasize in doing that was just they're really two parts of a single problem that lets Newton's laws help you figure out how forces act to change the motion of an object. The same thing is true when we think about rotational motion. When we think about using Newton's laws to describe rotational motion, there's still two pieces. There's a rotational dynamics piece, there's a rotational kinematics piece, but they're really both just two parts of how Newton's rotational law is telling you how forces act on an object to cause it to spin. And so what we're going to do is flip it up a little bit. We're going to start by introducing the rotational kinematics piece first, and then we'll come back and focus on the rotational dynamics. Just like we did with our translational motion, where we limited ourselves to thinking about two types of motion, we're going to do the same thing here. We're going to limit ourselves to thinking about either motion with a constant velocity or motion with a constant acceleration. And so when we did the translational version of these problems, we said with translational motion, we had a single equation. If you have a constant velocity, there's only one equation that tells you that your final position in x is equal to your initial position in x times the x component of your velocity times time. So as a one-dimensional problem for an object moving in the x direction with a constant velocity, there was our equation. For rotational motion, there's a very similar equation. There's a couple key differences. The first, most obvious one, of course, is that we've swapped out our translational variables for rotational ones. So our x position has become a theta angular position. Our v velocity has become an omega angular velocity. The other detail that's worth pointing out is that, again, this is motion in the x direction. This is rotational motion about the z-axis. So that's why we've changed our subscripts here as well. So this tells us that we're going to draw things out in the xy plane so that vectors describing the motion are defined along the z direction. For our rotational motion problem, we're very, very rarely interested in the actual angular positions. Instead, what we're almost always more likely to be interested in is the angular displacement. And so we'll just go ahead and rewrite this equation right up front in terms of the angular displacement. So we have one equation that describes translational motion with a constant velocity, one equation that describes rotational motion with a constant velocity. And again, these equations only work if the acceleration is zero. So here, our linear acceleration is zero. For our rotational motion equation, our angular acceleration has to be zero. For motion with constant acceleration, we said if you have constant acceleration, we have more equations. And so for translational motion, we said there were three of them. There was an equation that told us about position as a function of time. There's an equation that told us about velocity as a function of time. And then there was an equation that we had eliminated the time from that sort of laid out what was going on in terms of all of our other variables. Again, for rotational motion, it works out that there's a set of three very similar equations. And so again, we've changed the x's to thetas, we've changed the v's to omegas, we've changed the a to alpha, and again, instead of this being motion in the x direction, this is now rotation about the z-axis. So we've changed our subscripts as well. We'll do the same thing we did up before and say, well, let's go ahead and reframe these equations in terms of the angular displacement, because that's almost always what we're actually going to care about rather than some absolute angular position. The equations on the left for translational motion, again, those were only valid when the acceleration was a constant. The equations on the right for rotational motion, same thing. These are only valid if your angular acceleration is constant. And so we need to keep that in mind in terms of whether or not we're using these equations. So when we go to work rotational kinematics problems, we're actually going to start the same way we did with translational kinematics problems. We're going to say, well, what do I know? And in this case, because we're sort of collapsing both those position variables into a single angular displacement, there are basically four vector quantities that we want to think about what we know about them, and then there's our scalar of time. Once we've laid this out, we're going to ask ourselves, was the angular acceleration of the object zero? Because if the answer is yes, then we only have a single equation that's going to describe what's going on with the motion. On the other hand, if the angular acceleration is not 0, then we've got to follow through and say, well, is it constant? Because of course, if it's not constant, then we can't use those constant acceleration kinematics equations. Instead, we've got to figure out some other way to work the problem. If it is constant, then now we need to think about, well, which of those three equations is likely to be the most useful one to deal with. And so, of course, just like before, that really revolves around time. If you don't know time, you aren't asked to solve for time, you think you can get away without knowing time, then probably what you want to do is you want to go ahead and use that omega squared equation, so our equation that doesn't have time in it. On the other hand, if you do know time, or that's what you need to solve for, then again it becomes a situation of, well, do you know more about angular displacement or do you know more about the angular velocities? And so if you know more about angular displacement, then we have the angular displacement as a function of time. That's probably going to be your best equation. If you know more about the angular velocities, the initial and final angular velocities, then you want the velocity as a function of time equation. How we sort of make these abundance of equations work for us is in some sense just letting the information we have help lead us to what's the most likely equation that we want to use to start working a problem. So let's look at an example. And again, we're going to start by looking at an example for translational motion. So this is a problem that we actually have already looked at, that's sitting, back in your notes, back from some video that you watched multiple weeks ago. So we'll work through it quickly. But what I want to emphasize is the process we're going to use to solve this problem as a one-dimensional translational motion problem is going to be very similar to what we're going to do in solving our rotational kinematics problems. So here we're told that we've got a motorcyclist. He's traveling along a long straight stretch of highway. Initially he's traveling with a speed of 25 meters per second. The road sign informs him that he's approaching a small town and needs to slow to a speed of 10 meters per second. If the small town is 300 meters past the road sign and he slows at a constant rate, what is the cyclist's acceleration? How long will it take him to slow down? So we're going to start the same place we did before. We're going to draw in an initial picture and a final picture. And again, we're going to go ahead and draw in the vectors. So our initial position vector is a 0 vector. Our final position vector points in positive x and has a magnitude of 300 meters. Our two velocities point in the positive x direction. But of course, because our object is slowing down, the acceleration points back in negative x. So we've drawn our initial position, our final position, and the vectors that we're going to use. And of course, we needed to pick a coordinate system to do that. And so I've just said, well, let's let the origin be where the motorcycle is initially, and let's let positive x be the direction the motorcycle is moving in. So now we want to think about what we know. And again, I know both my initial and final speed. I know both my initial and final position. What I don't know is the acceleration or the time, but I do at least know that the acceleration has to point back in the negative direction. So that's what this negative sign here is trying to help me keep track of, which is when I solve for A, I better get a negative value. If I don't, then my answer doesn't make any sense. There's got to be a mistake in there somewhere. And notice there are two unknowns sitting in this table. So the first of those unknowns, the acceleration, lines up pretty well with the first question I was asked. What's the cyclist's acceleration? The second unknown, time, that's the second equation. So the nice thing here is I have two unknowns, I have two equations, they match up perfectly in terms of those equations are asking me to solve for those unknowns. So let's take my table, and so now think about, well, how do I want to go through solving this? So let's start by solving for the acceleration. I know I have a non-zero constant acceleration. I don't know time, so let me see if I can get away without knowing time. So I'll start with my v squared equation. I solve that for the acceleration, plug in my values, I get negative 0.875 meters per second squared, and so sure enough that negative sign makes me feel pretty good about this because I knew I needed a negative answer. Now that I know the acceleration, to solve for time, I could use either of my time functions. Of course, the one for velocity is linear rather than quadratic, so it's just easier to deal with. So I can take my velocity function, solve that for time, plug in my values, and I get the time as 38.6 seconds. So this was our process for working a one-dimensional kinematics problem with translational motion. Now let's look at a rotational motion problem. And again, it's going to be a one-dimensional problem because we're only going to be interested in vectors that lie along the z-axis here. And so what we're told is we've got a food processor whose blade can spin at variable speeds. Initially the blade's spinning with an angular speed of 25 radians per second. We switch the processor to a slower speed of 10 radians per second. If the blade rotates through 30 radians as it slows at a constant rate, what's the angular acceleration of the blade? How long will it take the blade to slow down? So again, I'm going to start where I did with my translational problem. I'm going to draw myself an initial picture that shows what's going on. I'm going to draw myself a final picture. I want to come back and think about those vector quantities that I care about. So the first one's going to be the displacement, and using my right hand rule, I see that since I've drawn this so that my blade is spinning counterclockwise, then when I rotate the fingers of my right hand counterclockwise, my thumb points out, which tells me that the angular displacement points out. Again, initially, because that blade's rotating counterclockwise, that means the initial angular velocity points out. My right hand rule tells me that it's still rotating counterclockwise, so the final angular velocity also points out. But since it's slowing down, I know that the angular acceleration has to point in. So in terms of the four vector quantities that I'm going to care about, I know which direction all of them point. I need to pick a coordinate system, and so given the fact that three of them point out, I'll let positive z point out. So at this point, I want to think about what do we know? And I know the initial angular speed of the blade, the final angular speed of the blade. I know the angular displacement of the blade. What I don't know are the angular acceleration, though I do know it needs to be negative when I solve for it, and I don't know the time. And so again, I've got two unknowns here, and those two unknowns match up with the two things I'm asked to solve. Take my table, think about, well, let's see. I want to solve for the acceleration. I'll start solving for the acceleration first. I don't know time, so again, let me see if I can get away without knowing time. So if I use my equation for omega squared that doesn't involve time, solve for alpha, I get that the angular acceleration of the blade is negative 8.75 radians per second squared. And again, that negative sign makes sense. I knew that that acceleration pointed in the negative direction. Well, now that I know the acceleration, again, I could pick either of my time functions to solve for time. I'm going to use the one for the angular velocity because, again, it's linear, not quadratic, which makes my life easier. And so I'll solve for t, and I get that t is 3.86 seconds. What we're doing with our rotational kinematics problems is not really anything new. All we've done is we've just changed that instead of a translational motion in a single direction, we have a rotational motion problem about a z-axis.